Welcome back. We are entering the fourth chapter, thermochemistry. Not a particularly long chapter, it's not a particularly hard chapter, but it's still a very necessary chapter before we get to chapter 5. This is just to show you kind of how we've expanded on some of the science that we covered in general chemistry. So once again, we're going to cover delta H and delta U and Q equals MCAT, and we're going to take that a little bit further. See how we actually need to treat chemical reactions. So we would find in general chemistry the enthalpy of reaction by looking up the enthalpy values in the table. We're going to take that one step further because physical chemistry is always a step beyond general chemistry. Last couple chapters, we looked at just the energy to heat up and cool down solutions. Now we're going to actually look at the heat involved in chemical reactions. So, remind you, enthalpy, delta H, is calculated most commonly at a constant pressure system. But we can use enthalpy to calculate internal energy. That is not any problem. We have they're both a function. They're both a function of temperature, with delta H coming from a depending on temperature and pressure. So now, in general chemistry, we calculated the enthalpy of a reaction, assuming constant temperature and constant pressure. We said, oh, how much energy would it take to react hydrogen with oxygen and form water? Well, now we're going to take that a step further and calculate the enthalpy of that, maybe at a different temperature, and the enthalpy of that may be at a different pressure, because not always are we going to use 1 atmosphere. Not always will everything be done at 298 Kelvin. So we need to be able to calculate how that will affect things. And so that's what some of the functions we're going to use will help us do. Every compound will have a specific internal energy and enthalpy. But because they're a function of temperature and pressure, we're going to tabulate these values at standard temperature, standard pressure of 1 bar in order to make them comparable. And when we're doing this at the standard conditions, we give that little knot or circle above that. So delta U naught and delta H naught are internal energies and enthalpies calculated at 298.15 Kelvin and 1 bar. So the enthalpy of a reaction at specific temperature and pressure can be defined as the heat withdrawn from or transferred to the surroundings to turn the reactants into products at a constant temperature and a constant pressure. Quick reminder, exothermic reactions would have a negative Q, endothermic reactions would have a positive Q. So heat absorbed, positive Q, heat released, negative Q. So we're just looking at this thought experiment. If I turn iron oxide with magnetite and react it with hydrogen gas to reduce this to iron and water. So we could think of this as several different steps. So we allow the reaction to occur at a constant pressure, adiabatic walled, container where no heat flow is allowed. The temperature of the system changes from 298 to some temperature T. The reaction heats up. Now the walls are allowed to turn into diathermal, which allows our heat to flow through the walls. The container is submerged into a water bath at 298. Heat will exchange until we get the water bath and the reaction vessel back to thermal equilibrium. So the reaction vessel will cool down, the water will heat up. Now, unless the reaction vessel has cooled down. Now, the change in temperature of that water can be measured. And if we compare this to an electrical heater, use an electrical heater to bring the temperature of the water back to where it was, we can use the energy of that electrical heater and compare it to the energy, the enthalpy of that reaction. So if the water bath cooled down, we can use electrical heater to heat it back up. And if the water bath heated up, we can use an electrical heater in a separate water bath to heat the water till it's the same temperature. And that way we can find out how much energy of the reaction occurred. Now, while this could not be conceivably done for every reaction combination, it can be done with every reactant and every product individually. So, while we can react iron oxide with hydrogen, we can maybe react iron oxide with oxygen, but can we react this with every single physical possibility to find every single reaction? No. But we can react each guy individually and find out some facts about each individual reactant and product. So generally speaking, we can calculate the delta H of a reaction by summing up the individual enthalpies of each product and subtracting the individual enthalpies of each reactant. So hypothetically speaking, notice not delta H, but H of a reaction, H naught of a reaction would be the 3 times the molar enthalpies of iron, 4 times the molar enthalpies of water, minus 4 times the molar enthalpy of hydrogen, and minus 1 times the molar enthalpy of magnetite. And that would be calculating the H of the reaction. Now, there's a problem here in that there's not really a useful way to calculate the absolute enthalpy of reaction because there's no experimental way to find the absolute enthalpy of any given element and compound. Because it's like, how do you measure distance without first setting a standard to measure this by? Without a ruler, you can't say like, well, this is 12 feet long without first having a ruler to measure the feet. So even if you like used a body part right there, you're still, without that first, you have to have something to measure it against. There's no absolute zero here. So we need to calculate a relative change in enthalpy and a relative change in internal energy rather than the absolute values. So we'll use a delta H formation values, the energy needed, and we're going to define that as the energy needed to form 1 mole of a product from the pure elements in their standard state. So iron oxide, magnetite would be how much energy would it take to form magnetite from pure iron and pure oxygen. Water would be how much energy does it take to form water from pure hydrogen and pure oxygen. Iron, being an element of its standard state, would be just iron itself. Hydrogen, being an element in the standard state, would be itself. So that makes things a lot easier. Because of how we're defining this, pure elements will always be zero, because how much energy does it take to go from iron to iron? Same state, zero energy. It's the cyclic rule of state functions. If I go from 1 to 2 and back to 1, you're going to have zero. Zero enthalpy, zero internal energy for a state function. Because whatever this value is, if this is 50, 50 minus 50 is still zero. Iron oxide will not be zero because it takes 3 irons and 2 oxygens to make iron oxide. So we can calculate the heat of formation of magnetite because whatever this value is, say it's 25, well, this value is going to be, well, as I said, 50, 3 times 50. Maybe this is 12 minus 2 times 12, and you can figure that out. Whatever this value is and whatever these values are, you can figure that out and calculate a delta H value for a compound. Same thing can be done for water. Going back to this reaction, the hydrogen drops out, the iron drops out, and so this reaction simply becomes 4 times the delta H molar formation of water in liquid state minus 1 times the standard state enthalpy molar of formation for magnetite. In general, we're going to write this for any delta H reaction. So this is a little funny from what we're used to seeing, but this is what we were doing in general chemistry. It's the sum of the delta H formation values times this V, this nu, is the molar coefficient. So in iron oxide, it's 1. In water, it's 4. But here's another thing, and that a product is going to have a positive V, and a reactant is going to have a negative V. So what this is saying is 4 times this delta H minus 1 times this delta H. And so that way we can combine this products minus reactants into one quick little phrase. You're adding them together by putting that nu, that little swirly V in there. And there's one more reference point we need to consider, in that when we deal with cations and anions in aqueous state, how are we going to treat that? I mean, we can measure sodium chloride solid. How do you measure sodium ion and chloride ion? Because once again, the reason we couldn't have a measure absolute enthalpy is because we didn't have a 0 point to measure anything up against. At this point, well, we don't have a 0 point to measure a cation without an anion. There is no magical cation you can produce without producing some sort of anion. So once again, we're going to set an artificial 0 point. We're going to say hydrogen splitting into a proton and electron on a metal electrode. And we're going to say that reaction, that proton is going to be a 0 kilojoule reference point. So any pure elements in their standard state will have a 0 delta H formation, and hydrogen electrode, the proton will have 0 delta H formation. Well, from this we can measure the cation. So we can measure the separation of HCl to get Cl. Then we can measure NaCl to get Na, and then Na to Br, and so on and so forth. And you can keep going down the list till you have all the cation and anions. because we're measuring it off a 0 point that we've set, hydrogen. So the delta H is path independent as a state function. It means we can calculate any delta H reaction as long as we have the tabulated delta H formations. But let's think about how we get some of these. Take the formation of ethane. If you calculated this ethane from the delta H formation rules, you'd say 2 carbon plus 3 hydrogen gives you ethane. Now, while this seems simple in practice, to actually do this in a lab would be impossible, because you're going to get a wide variety of products. Ethane isn't necessarily the lowest energy product, and once you produce some of the other products, it's going to be irreversible reactions. So you're not going to get 100% conversion to ethane. You might get 75% or 50% conversion to ethane, and you might produce things such as methane, propane, butane, isopropane, propene, who knows, ethene, ethine. Who knows what we're going to form? We're not going to form just ethane. So if we tried to measure this in the lab, this would be impossible. Because just because we have the right amount of reactants to give 100% conversion doesn't mean we will always get 100% conversion and complete conversion into what we want. So how could we calculate ethane by itself and not have to always consider the mixture of side products? And that's where Hess's Law came in. We learned this in general chemistry. It probably went over a lot of people's heads in general chemistry. But the general idea is that we can test the reaction that we want by comparing it to other reactions that we can know for sure because of the state functionality of enthalpy. That as long as the starting conditions and the ending conditions are the same, it doesn't matter. So we're going to look at 3 reactions. Carbon's oxidation to CO2, which is known and can be fully converted with ease. Hydrogen's conversion to water, which can be known and done. And ethane's combustion, which can be fully converted to CO2 and water. If we do that, and we know those values. So what do? We need 2 carbons here, so we do this reaction twice. Because of the nature of this, if I double this reaction, I would, since it's an extensive property, I'd double the heat produced there. And I have 3 hydrogens there, so I need to do 3 hydrogens. So once again, I would triple the energy from that reaction. And because I have ethane as a reactant here and ethane as a product there, I would have to reverse this reaction. So if it produces 1,561 kilojoules combust ethane, it must absorb 1,561 kilojoules to split it back apart into ethane from CO2 and water. So if I multiply the coefficients through, add all of them up, the O2s cancel out, the CO2s cancel out, the waters cancel out, leaving us only 2 carbon, 3 hydrogen, and 1 ethane, making this the same starting, same ending conditions. Doing the same with the delta H's. 2 times that, 3 times that, -1 times that, we find here's the heat of formation of ethane. There we go. That's all you need. And it doesn't even matter that that carbon monoxide can be a side product of CO2, because as long as you keep oxidizing, it will always fully convert. C plus O2 goes to CO. CO plus more O2 goes to CO2, such that 110 plus 283, negative 283 gets 393. So it doesn't matter if I have to worry about that. As long as I add enough oxygen, it'll keep converting. So we actually need Hess's Law a lot more than we think. Any new compound can have its enthalpy tested by Hess's Law, so long as we know what it reacts with and we can measure the delta H of that reaction. So all that was basic general chemistry stuff. Now we're going to take this a step further. So until now, we've only calculated delta H at 298. But what if the reaction doesn't occur at 298? How do we deal with that? So first, we break it down into, we look at the reaction at 298, and then we adjust the enthalpy to the new temperature using our Cp delta T. We've done this before. So, we say, here's our starting enthalpy of a reaction, and then we modify it up the temperature. So just like we did in chapter 2 and 3, we're just adding on the delta H of reaction. Delta H new temperature would be delta H at 298 plus the integral of 298 to the new temperature of Cp delta T. And Cp delta T, now here's where it gets a little hard. We have to take the sum of all the CPs of a given reaction, because each reactant, each product will have a different heat capacity. So if one of these needs a lot of heat to heat up, it's going to affect it more than a guy that takes very little energy to heat up. So if you have some gases which have low heat capacity and some liquids which have high, it's going to play wonders with how much heat is needed to make this work. Once again, positive V for products, negative V for reactants. And a generic T is used here to distinguish from variable T. The T prime here is used to distinguish from the variable T of what the actual T we're measuring in the integral. So the delta Cp T prime dt prime is used to say like a function of the generic temperature, not function of 29, let's say temperature 500. Okay, the function of temperature, and T here would be 500. So let's just look at this. So so we have thermite at reaction 25 and 100. Quick, I'm going to do that. Hold on, grab my book out here. I need to look up all this crafty crap up in the thermodynamics. So first things first, what's our delta H? Delta H of aluminum, that's 0. I can tell you that right there. Iron, oh, that's 0. That's convenient. But iron oxide and aluminum oxide. Aluminum oxide, negative 1675.7. I'm going to go ahead and write these down so I don't forget it. $79. Okay, iron oxide, moving to iron. Iron. The iron is 0, the Cp is 25.1. Fe2O3, delta H is 824. Q. And the 203, the heat capacity of this guy is 103.9. 103.9. So first, finding out delta H naught. Delta H naught is equal to negative 1675.7 times 1 and negative 824.2 times negative 1. And of course, iron is 0 times 2. And of course, 0 times negative 2. I'm going to include all things, iron and aluminum. But basically, the delta H for this guy, negative 1675.7 plus 824.2. If I did this at room temperature, I would have negative 851.5. That's our first energy. Now, what happens if I do this at a higher temperature, at 100 degrees? So we have to add in our CP delta T. Our delta T is just going to be 100 minus 25, so 75. Our CP is going to be 25.1 times 2 plus 79 times 1 plus 24.4 times negative 2. That's 103.9 times negative 1. 2 plus 79 minus 24.4 times 2. 103.9. So our CP, our delta heat capacity, is equal to negative 23.5. That is joules per mole Kelvin. So actually that's joules per Kelvin. Because we are kept the 2 and the 1s are all factored in the moles. So 23.5 times 75 divided by 1,000 means we're going to drop by 1.76 kilojoules. Or actually, so the energy is going to go up by 1. So our new delta H at 100 is negative 853.2. So it was already spontaneous, already a big energy boost, but at 100 degrees, it's even more energetic. So now that may think, oh, that's barely a change. Barely a change. But that considering it's only done at 100 degrees Celsius, boiling water temperature. It's only going to go up as the change in temperature goes up. Say we're trying to do this at 500 degrees. Suddenly 2.5 times. Suddenly we've jumped up by 11 kilojoules. And the hotter you get, the greater the change is going to be, the greater the effect. So now, how do these delta H and delta U get actually measured? The most common way to test these are with a bomb calorimeter. A bomb calorimeter will be used to measure heat flow from a reaction into a water bath and thus determine the energy released. Now there's two types of bomb calorimeters. There's constant pressure and constant volume. The constant volume are very useful for gaseous reactions. Ones that you combust something. You put some food in there, you put some sort of a hydrocarbon in there, you burn it, it produces gases. They're all contained in the container. So even though the pressure of the container goes up, the volume of the container has not changed. It's constant volume. And because delta U is a function of volume and temperature, it measures delta U, the internal energy of a reaction. Constant pressure ones are great for solutions where it's open to the pressure, open to the atmosphere, we're allowing things to mix together, and we're allowing them to produce heat. Oh, geez. So constant volume one. Since this is essentially an isolated system, the internal energy is zero within this calorimeter. Meaning the heat flow will be completely absorbed by the water bath and by the calorimeter itself. We're not going to see anything lost out. So we have a motorized stir to keep this uniform. We got a thermometer to measure the actual heat change of the water bath. Ignition wire is going to do this reaction. So when that burns, sample cup, we're going to see how much this heats up. So because delta U for this whole isolated system is equal to the mass of the reactants divided by the molar mass times the delta U of the reaction. The mass of the water divided by the molar mass of water, that gives us moles of water, times the heat capacity of water, times the temperature of the water bath, but also the heat, we have to consider the heat capacity of the calorimeter. The mass of the calorimeter will not change, and the temperature change of the water bath is also going to be the same as the temperature change of the calorimeter. But this whole system is zero. So if we know how much heat capacity of water is, we know how much water we have, we know how much the heat capacity of the calorimeter is, then by measuring the temperature change, we can figure out our delta U reaction. So for most systems, then you could use your delta U reaction to find delta H. Because remember, delta H equals U plus PV. Well, PV can be exchanged for nRT. Well, temperature is going to be the same for that gas, the uniform for that gas. So delta N is how many gas molecules have been made. The change in gas molecules will calculate the pressure for that. And thus, we can figure out the delta H of the reaction just the same. This will be a useful reaction later. Constant pressure, same thing. We have a thermometer. We have some sort of tube, insulated water bath. We drop something in there to make it react, stirring, soak the heat. Same thing, delta H is zero for this isolated system. So it's impractical to use a constant volume for solids and liquids because the volumes of these guys will change when I mix these guys together. The only way to the only major difference in this reaction is that we find delta H instead of delta U. Other than that, it's the exact same reaction. Okay, so practice problem in here requires us to use our book again. We're doing a bomb calorimetry problem for nickel chloride reaction. Dissolution to, so okay, our reaction is nickel chloride solid breaks down into nickel 2 plus and 2Cl minus. Aqueous. And we're asked, what would the temperature change be if I did 50 grams of this into 100 grams of water with a calorimeter with this heat capacity? So normally we'd calculate the delta H given a temperature change, but we're doing it in reverse here. So, because we're expected to, so 50 grams of nickel. Nickel is molar mass of 129.62. And we need to find the delta H, 305.3. And nickel 2 plus is negative 54. Chloride 1 minus is, nope, that real quick, negative 167.2. There's two of them. Negative 305.3, flip the sign, negative 54, and negative 167.2 times 2. So the delta H of this reaction is negative 83.1, and it's in kilojoules. And so divided that by 1,000 times 50 divided by 129.62. We get the first term, negative 32,055. Our water term, 100 grams of water, 18 grams per mole. And now the heat capacity of water for this, okay, you might be tempted to say 4.184, but that is the heat capacity for grams of water. Heat capacity for water, liquid, the molar heat capacity is 75. 318 times 25.3 is 418.33. We're going to add that to 342.5. All that delta T. 342.5. You get 760.83. And delta T, find delta T. All this is equal to 0. So I'm going to get the negative 32055 to the other side. 2055.2 divided by 760.83. That leaves us with the delta T would be 42.1. 42.1. Okay, let's see. So, okay. Okay, that's essentially, there's one other tool we can use in the trade right here, and that's the differential scanning calorimeter. Now, while the bomb calorimeters measure the delta H of reaction, the differential scanning calorimeter does something completely different. It will measure the heat flow as a function of time in comparison to a reference point. So it's going to measure your heat capacity and see how it changes in a material as it undergoes a whole heating curve, because heat capacity actually can change. And if a sample does something, like does various reactions, it will change drastically. So if you set essentially the machine is going to measure the heat of a sample versus a reference, and you set a specific heating rate. So you want your sample to go up by that much temperature, that much time. It's going to adjust the heat flow into or out of your sample to keep it even with the reference point. Now, if the heat capacity is constant over the temperature range, the heat flow will be constant, and you'll see a straight line. But when you start to get something interesting, like a phase change or chemical reaction, you'll see the heat flow will change drastically. And because it's changing properties. So, like for example, a glass transition. So it's changing the crystal structure of your compound. And so suddenly you see a drop in heat capacity or a jump up in heat capacity. If it crystallizes, all of a sudden you see a jump up. But suddenly, as it crystallizes, it releases heat, so suddenly it doesn't need to put in as much heat to keep the temperature same. Melting point. If it melts, you're going to see that's something it's going to absorb a lot more heat, so you're going to see a lot more heat flow needed to keep the rate the same. If it becomes cross-linked, so like it starts to form bonds between different between itself and other intermolecular bonds to secure it together, you'll see a jump. And oxidation, you might see it just peak off and eventually it'll die. So essentially, you could do multiple cycles to see if this is a reversible phase or not. Like cross-linking, you can't really reverse that. Oxidation, you can't really reverse that. But crystallization and melting, you should be able to. Yeah. The only problem is because the instrument doesn't instantly adjust. It takes a while to figure this out and fix things. These changes will come as a broad peak. So the crystallization is not just one sharp jump up. You see a gradual like, oh, it's taking more energy, so I'm going to start putting in more energy. Okay, it's peaking up and it's going back down. Calm it back down. But if you take the integral under that curve, you can still get the delta H for this phase change. So if I integrate from here to here and measure the area under that curve, the area above that curve, you can figure out how much energy would be in that phase change. So these are very interesting technology if you know how to use it, know how to read it. That is all for this chapter. It's a very short chapter.